The Simpson's rule. Let's see what happens only on one subinterval for which the function is concave down and up. Let's start with concave down. Approximation by midpoint rule gives me more than the real area. On the other hand, the trapezoidal rule gives me less than the area. And here's the combined rules. When the function is concave up, then on this specific subinterval in which the function concave up, we get that the midpoint rule is now less than the real area, and the trapezoidal rule is more than the real area. And here's the combined one. You can see clearly that the area, the real area, is always between the two approximations. The Simpson's rule. Because the error of the midpoint rule is half of the error of the trapezoidal rule, it makes sense to make a weighted average of the two rules, where the better one, which is the midpoint rule, is weighted twice the other one, which is the trapezoidal rule. First, we are going to apply the midpoint rule on all x's with even indices. Note that the x's with odd indices are the midpoints of two consecutive x's with even indices. And we're going to apply the trapezoidal rule again only on the x's that has even indices. Then we're going to do the weighted average. So you can see here that first of all that we can apply the Simpson's rule only when n, which is the total subdivision to n parts between a and b, is even, because we are applying actually the two rules only on half of the points. Note again that n must be even, and we are applying the two rules on half of those points between a and b. So again, we note that each of the x's with an odd index, x sub I, is a midpoint of the subinterval x sub I minus 1, x sub I plus 1, where I minus 1 and I plus 1 are consecutive even numbers. So here's the midpoint. Okay. We are using here a little bit of algebra. And now let's apply the trapezoidal rule. Again, only on half of the axis. Okay. Again, the subdivision is 2n over 2 parts. We get that. And we can cancel out the 2's here. And we get that. Now let's do the weighted average. As we said before, we are going to count the midpoint twice and the trapezoidal only once. So it is 2, the midpoint, plus 1 time the trapezoidal, over 3. Let's substitute for that, and we get this. Now we will multiply everything by 2 in the first part. You can see that you can distribute b minus a over n, and we get that. Now we just want to reorder. Here is by the order of the indices. We want that the first one will be f of a, and then f of x1, and then f of x2, and so forth. After ordering, we are getting this. And we get the Simpson's rule. And now pay attention to the pattern. We have delta x over 3 times. Now we are writing f of the first, x0a, and then the second, the third, and the fourth. And you can see that there's a pattern. F of a and f of b appears only one time. And then between them we have alternation of 4 time and 2 time, 4 time and 2 time, and so forth, till f of b. Example. Let's use the Simpson's rule with n equals 8 to approximate the integral between 1 and 3 of fx dx. Let's do everything on the x-axis. Delta x is 1 over 4, and we get that. Now we really want to pay attention how many times we have to multiply f of the x's that are appearing here. F of 1 should appear 1 time, and so is f of 3. F of 1.25 should appear 4 times. This one 2 times, 4 times, 2 times, 4 times, 2 times, and 4 times. Delta x over 3 is 1 over 12. So we get the approximation by 1 over 12 times 1 time f of 1, 4 times. The next one 2 times, the one that is next, then 4 times. F of the next one 2 times, f of the next one 4 times, f of the next one 2 times, f of the next one 4 times, f of the next one, and the last one appears only once. Here is the error bound for the Simpson's rule. Now we are looking at the fourth derivative of the function f in absolute value. And k4 is the number such that the fourth derivative of x in absolute value is less or equals than k sub 4 for all x's that are greater or equals to a or less or equals to b. Then the error bound of the Simpson with n subdivision is less or equals to k sub 4 times b minus a to the power of 5 over 180n to the power of 4. Example. Let's find the minimal value of n for which the error for the Simpson rule approximation for the integral between 1 and 4 of cosine x dx is at most 10 to the negative 12. Here is the setup. Now we need to find k4. In this case it's pretty easy. All the derivative of cosine x are cosine x or sine x plus or minus, but in absolute value any nth derivative cannot exceed 1. It means that k of 4 is 1. And we get that. Pay attention that b is 4 and a is 1. We get that. 180 is divisible by 9. Okay, so we are writing 180 as 9 times 20, and we write 3 to the power of 5 as the product of 9 and 3 cubed. Now I would like all that to be less than 10 to the minus 12. I get a very simple inequality with capital N, so we are just going to solve that. I multiply everything by n to the 4, and then I multiply everything by 10 to the 12, and I get that n is at least the fourth root of 27 over 7 times 10 to the power of 3. Here are all the error bounds for the trapezoidal, for the midpoint, and for the Simpson. The Simpson rule is much smaller error bound, which means it is going to be better approximation. Example, find the minimal value of n for which the error for the midpoint rule approximation of the integral from before is at most 10 to the minus 12. Here is the setup. I would like to recall that case sub 2 is 1. And now we would like all that to be less than 10 to the minus 12 as before. And we are going to solve that exactly as before. Multiply both sides by 10 to the 12th and n to the power of 2. And we get that n has to be at least radical 9 over 8 times 10 to the 6. The Simpson's rule is more accurate and it's much more efficient process of the approximation than for the Simpson rule. We need n which is more or less 10 cubed, while using the midpoint we will have to use n which is more or less 10 to the 6. Example, find the smallest n for which the error when using Simpson's rule for the integral between -1 to 1 of e to the negative 2x dx will be at most 10 to the negative 10. Here is the function. Each one we are applying a derivative, we get negative 2 times the derivative that before, so after 4 times, we are going to use 4 times the chain rule, and we are going to get 16e to the power of negative 2x. We want now to bound that. It's always a good idea not to have negative exponents, because this is a decreasing function and e to the 2x is in the denominator. Then we make it larger if e to the 2x is the smallest possible value when x is between -1 and 1. It's obvious that e to the 2 times -1 is smaller or equals to e to the x on this interval. And we get that. We don't need absolute values, because e to the power of anything, it's always positive. We rewrite this as 16e to the power of 2, and this is our case sub 4. Here's the setup. B is 1, A is -1, and case sub 4 is 16e to the power of 2. Get that. And that, just calculations. And I want this to be less or equals to 10 to the power of -10. We get this. And we get this. And we know that n has to be greater or equals to this number. Don't forget that n is an integer, so we can even say that n is the smallest integer that is greater or equals to this number. If this number is not an integer, then n will be strictly more than this number.